differential control volumes. So you're gonna see, if you look at the book, that the book has things a little bit more mixed up. And the reason I'm teaching it this way is because if you understand the energy balances and you understand the heat transfer mechanisms, right then we can do lumped capacitance that has an enormous practical value. Lumped capacitance depended on the condition that all the temperature is uniform inside the control volume. That is true in many cases, and today we're going to see in what cases that is true. But in some cases, might not be true. And how do we work then? So for the work energy balances to be practical, typically we want to have the temperature inside to be uniform. If the temperature inside a body is not uniform, then we can do an energy balance that is so small, is differential, such that inside that differential we can say is constant. And then the problem is very similar to the lumped capacitance that we saw last week, except that is lumped capacitance point-wise inside the body. So now the problem became a lot more complex, because to solve it, we need to solve partial differential equations, not just the ordinary differential equations we had before. What I want to do today and this week is to get to the point in which we do the same exercise we did for lumped capacitance, but for smaller volumes, and we'll end up in a differential equation. At this stage, we will not solve the differential equation, but I want to make sure that we know where those magical equations come from. So let's see. Let's start with the surface energy balance. And in this case, we're going to make a control volume that captures only the surface of a body. And it's a body in which this control volume is going to be a closed control volume, in which we don't have mass coming in or out. We don't have advection and we don't have evaporation. This is just, let's look at the surface of a body like this. Whoops. Like this one here. And we see, on one hand, we have, let's say, a solid, could be a liquid too, on the left. On the other side, we have a different condition that can be, in this case, for example, a fluid such as air, or if this was solid, can be a liquid on top. And if we do this control volume just over the surface, and it's very thin, some interesting things happen. In this control volume, we capture a chunk of surface, or all the surface, if the temperature is uniform on that surface, but the thickness of this is infinitesimal. It's a differential control volume. So we can do Q in minus Q out plus Q generated equals a Q stored. Because this is so small, it has a finite area, but it has such a small volume, we have the Q generated that is generated in the volume is 0 because we have no volume. Similarly, the Q stored, that is, the heat is stored in the mass inside the control volume, when the volume tends to 0 in thickness, there is no Q stored. So in this control volume, we have that Q stored goes to 0, Q generated goes to 0, and we have Q in equals Q out, right? Or Q in minus Q out equals 0. And Q in this case, because we have let's say a solid on our left side, is by conduction. We have, let's say we have no advection here, and this would apply also to liquids. So the heat by conduction would be this cross-sectional area for conduction times the heat flux by conduction. These two terms, these are things we saw on week 2 of class. This goes into the quiz of Wednesday. I'm not going to ask you about the energy balance and how it generates a boundary condition, but this you should be able to do based on what you saw in weeks 1 and 2. So we have the cross-sectional area that is this area. Oh, I might have missed this. Oh, I thought I had uploaded them. Okay, sorry. Let me see. I thought I had uploaded them under differential control volumes. If they're not there, I will do it immediately after class. Okay, should be in E-class. Okay, so this cross-sectional area is the area of this surface on the solid side. Now, this heat flux due to conduction is this AC is K, is minus K, the gradient in X. We saw that in week 2 for heat transfer mechanisms for conduction. Now, what is Q out? Q out is the area of this surface that outside we call it AS, but we're going to see that the cross-sectional area here for conduction is exactly the same as the surface area for surface energy losses on the other side. And the heat flux in the surface. The heat flux in the surface can be many things. It could be convection, contact, radiation, because all of those had a similar expression that was an H times a temperature difference between the surface and the far temperature. Let's assume it's surface because it can be extrapolated to everything. Let's say it's convection. So this heat flux at the surface would be H time of the surface minus the fluid at infinity. If I get this equation 3, I put it in equation 2 to calculate Q out, and I have a Q in here, and I combine Q in and Q out together, I end up with this equation 4. And isn't this incredible? This expression can be intimidating because all of a sudden we have a differential expression. But we have to know that this didn't come out of nowhere. This came from doing the exact same energy balance we do all the time. And using the heat transfer mechanisms we saw in week 2 and we keep using all the time. So this is a boundary condition because it's the gradient of temperature at the surface equals the some coefficient times the difference of temperature between the surface and the fluid. This is a boundary condition. So we're going to see in 5 minutes from now how we generate differential equations. Differential equations need boundary conditions. And this is one of the boundary conditions. This boundary condition is called the Robin boundary condition. And what has interesting or challenging is that we have a gradient at the surface equals some other term that involves temperature at the surface. There are other type of boundary conditions. For example, the Dirichlet boundary condition, in which you say my surface temperature is so much, done. That's a very easy boundary condition. There is another boundary condition called the Newman boundary condition, in which you say I specify only the derivative, right? And in this case, we're involving 2 in the boundary condition. We're going to see more on this later on as we start working with these energy balances and solving the equations. This same boundary condition would apply for the case of radiation if we use the radiation equivalent convection coefficient. So now that we have this boundary condition, we can address the question that we have been postponing all of last week. We said in lumped capacitance, we can do amazing predictions with relatively simple equations if we could say that the body is at uniform temperature. And I said, sometimes yes, sometimes not. As of last week, and for your quiz on Wednesday, you will assume yes, it's uniform. But you didn't know up to this second when it is uniform and when it isn't. So let's look at it now. And so I didn't get in time to type these notes, but here you have my best attempt at handwritten notes. So let's go back to consider the sphere we consider at the beginning of lumped capacitance. We have a sphere, and the sphere is in a fluid. There are two extreme conditions for putting a sphere in a fluid. In this case, we're cooling down the sphere. One condition is a condition in which the sphere is cooling down gently, so the temperature inside is more or less uniform. This is the case of lumped capacitance. So the sphere might be cooling down, and the heat is flowing from inside to the outside of the sphere, right? So to conduct heat, you do need a gradient. It's not exactly zero, but if it is almost zero, we're just gonna turn a blind eye on it and say it is zero, but it has to be small. That's one of the cases, this case up here. The other case is when the cooling is very intense. And when the cooling is very intense, then the surface, it gets cooled down to nearly the surface, the temperature of the fluid. For example, this case here would be the case of cooling the sphere in stagnant air, natural convection. This other case down here would be the case of blowing the sphere with a jet of water, very intense. So we have these two extreme cases in which what I'm hoping we're doing zero math right now, but to develop this intuition that although the sphere looks the same, inside it might be a completely different story depending on what case we're talking about. So let's talk briefly about the case in which the temperature is more or less uniform. So the center, if the sphere is cooling down, the center is going to be hotter, the surface is going to be colder, barely different, but not exactly the same. And this because we need to drive the heat by conduction inside the sphere. And I'm using a sphere because it's a very simple body to discuss, but it can be many things. It can be a plate, can be a cylinder, can be Mickey Mouse, whatever you want, the same conditions apply. I use a sphere because it's easy, or it's the easiest we can find to go over this concept. So the difference in temperature between the center and the surface is, I'm calling it delta T inside. Now, the difference in temperature between the surface and the fluid, I'm going to call it delta T outside. So in this case, the delta T inside is very small in the case of uniform, of lumped capacitance. In the case of very intense cooling, which we have not seen how to solve, but we will, we have that the center of the sphere is very hot, the surface is nearly the temperature of the fluid, and the delta T inside is very large, and the delta T outside is very small because the jets of water are cooling it down very intensely. So we have these two cases. And what would be the criterion for lumped capacitance? would be the case in which this delta T inside is much smaller than the delta T outside, which I wrote here. And a better way to express this is past this delta T outside dividing and to have this ratio, the ratio of delta T inside to delta T outside, to be much less than 1. Whatever this is dimensionless, and we're going to be using lots of dimensionless numbers in heat transfer. And okay, so let's see, can we ballpark this number here, this ratio, to see in what case we are? Based on what we just discussed about the surface energy balance, we made a differential control volume on the surface, and then we did an energy balance, and the conclusion was that the heat transfer by conduction had to match the heat transfer by convection, right? This heat transfer by conduction was the Q in, heat transfer by convection was the Q out. And we said in the differential control volume at the surface, Q generated and Q stored were 0. So these two are the same. So we had written it down and we said the heat transfer by conduction was this minus K gradient of temperature with the radius, and the heat transfer by convection outside is H delta T. And look, T surface minus T infinity is the delta T outside we were talking about here. This is the convection part is H delta T outside. And what is this gradient here, dt of dr? Well, let's do something that is an incredibly practical tool of engineering that enables us to cut through difficult math. And this is one of the main differences between engineers and mathematicians or physicists. Mathematicians will solve everything, but very often it's so impractical we don't want to use. Physicists tend to follow the mathematicians often. Engineers need to give an answer. The answer might not be perfect, but you must always give an answer. And by the way, these answers I'm sharing with you, those are awesome answers. They are not perfect, but they are perfect for the purpose we need. So what we are going to say is that this gradient of temperature, this radial gradient of temperature, is more or less the difference between the temperature at this surface and the temperature at the center over the radius. So we're turning this differential into a delta T inside over the radius. If we look again at our graph, would be the delta T inside over the radius. Is this exact? No, it's not exact, because delta T over delta R is not exactly at the derivative. But when the curves the curves are smooth, this is more or less right. Actually, we are off by more or less a factor of 2 that you're going to see is not so important when we were talking about orders of magnitude. And if you're interested more about this factor of 2, that was part of my PhD thesis. But let's forget about the PhD thesis. Let's forget about the 2. This is differential temperature over differential of radius is more or less delta temperature over radius. And this one here is delta T inside. So the right-hand side was H times delta T outside. That was the Q out. It's per unit area, because the area is the same on both sides. I canceled it out. On the left, we have the heat in per unit area. That is K times delta T inside over R. And if you see this minus sign that we have to have, this minus sign that appears here, because delta T inside, we take the hot minus the cold, so it would be center minus surface, and that's why we have this minus here. And because we have this minus here, goes away there. So now we have K times delta T inside over radius, heat in, equals H times delta T outside, that is heat out. If you remember, what we wanted to assess is this ratio, T inside, delta T inside over delta T outside. And this ratio now we can assess, and is HR over K. H convection coefficient times the radius divided the thermal conduction coefficient, thermal conductivity. This result is so general and is so important that it's being given a name. And the name it's being given is the Biot number. We will be using this Biot number a lot. And I wanted to share with you something that the book doesn't do, is where does this Biot number come from and what does it mean? So when can we have lump capacitance? When this ratio is very small, which means when the Biot number is very small. So now from today onwards, I'm going to assess if I can use lumped capacitance or not by looking at the Biot number. And this Biot number is going to be part of our language. I'll be saying it all the time. You might or might not remember the formula. It's so simple, but you'll know that you always go back to this. So if instead of a sphere, we have a wall, this would be thickness of the wall or half thickness of the wall. If we have a cylinder, it can be the radius of the cylinder. If we have a plate, would be the thickness or the half thickness of the plate, depending on the boundary conditions. We were going to see all those things in detail soon. But the bottom line is that you look at the Biot number, and from there you can say, I can apply lump capacitance or not. For quiz 2, that will be one of the questions you will be asked in the quiz. Can I apply lump capacitance to this problem? And conversely, if the Biot number happens to be very big, we are in this other case in which the surface temperature is more or less the temperature of the fluid. And this has important implications and makes our life simpler in a different way, a way we don't know how to deal with yet, but we're moving step by step. So now you know when you can use lump capacitance, not for Wednesday, not for the quiz on Wednesday, yes, for the quiz number 2. And you know when you can use this machinery that we have just studied or not. Look, very briefly, I have a cool example. If you know from people, if you have friends that in geology or in mining, you know that the Earth has a gradient. The deeper you dig into Earth, the hotter it is. And it's more or less 25 degrees C per kilometer. That's a lot. That's a lot, because when you're a few hundred meters under the surface, as people are all the time, it gets crazy hot, right? And this is one of the reasons why drilling deep is so difficult, because eventually you melt down the tools as it gets hotter and hotter. And it gets hotter and hotter because the Earth has this really hot core. So we here on the surface, we don't realize that much because we feel much more the effects of the atmosphere. But if we dig in, we start to have a sense of what's going on that is independent of the atmosphere, but all dependent on this hot core of the Earth. So we do have a gradient. We know that the Earth has heat conduction from inside to the outside. And the thermal conductivity of the Earth crust is more or less 3 watts per meter Kelvin. And this is tabulated, right? I didn't make it up. So the question is, what is the average heat flux coming out of the Earth? So we're using our differential energy balance on the surface. I know that whatever goes out of the Earth is the same as what comes in by conduction. And conduction per unit area is this expression here that we have seen in week 2. Plug and chug, and we get that heat conduction through the surface out from the center of the Earth outside is more or less 75 milliwatts per meter square. 75 milliwatts per meter square. What this means is that on average, the Earth is losing 75 milliwatts per meter square of Earth to the outer space. And of course it makes sense, right? When we are here, we see walls and we sun, and when we see sun and we see snow. But overall, the Earth is something that has this hot core and is surrounded by an environment at more or less 0 Kelvin. It has to lose heat. And this is what it's losing in average. And if you do the calculations, and I here put some more details, and it's fascinating because this thing we're doing here in class is what geologists do or geophysicists do for real. So now, if you say, how is the Earth losing heat to the space? Sure, it's not by convection, because there's no fluid in space taking heat away from Earth. We have a fluid that is a very, very thin layer of gas around the surface of Earth. If I lump this little surface of gas that is our atmosphere with the properties of the surface of the Earth, I would get a radiation coefficient for radiating into the surroundings at more or less 0 Kelvin of more or less 0.68. Right? That's more or less average the emissivity of Earth to outer space. And now, if you do that, you can calculate that you can calculate the temperature of the surface of the Earth as the balance between the energy that the sun brings in and the energy that is lost by radiation. And we don't have the time to get into detail of this problem, but please take a look at it, because it's fascinating how we can estimate the average temperature of the surface of the Earth just by doing an energy balance between the energy that the sun brings in and the energy that is being lost by radiation to the outer space. And it gives us, this calculation gives us actually the actual average temperature of the surface of the Earth. These equations we're working on are really powerful indeed. We have 6 minutes. I'm going to walk you through this other example that is really cool. We keep talking about differential energy balances, right? We said we can do a differential energy balance on the surface of the Earth, and we can relate the energy coming in from the hot core into what is radiated outside of Earth. Also, we can look at do a surface energy balance to understand an interesting phenomenon. I haven't seen much of this in Canada, but in places like my native Argentina, we don't see snow. I didn't see snow until I was grown. But you get to see frost. And an interesting thing is that frost happens even when the air is warm. This is an interesting thing. If I have air at 20 degrees C, how can I possibly have frost? I believe you're going to look at this problem in more detail in the seminar, but here I worked it out. Is this example here? And we do a surface energy balance. And the surface energy balance, we have that the heat losses through the surface are the same as conduction coming in. And we're talking about the roof of a house, and could be as well like grass, right, as we see in Argentina. But the surface of a house has an insulated roof. The roof is looking to space outside. In the middle of the night, if you have a summer night and it's 20 degrees outside, right, the roof is losing energy by radiation to outer space, and is not getting any energy from inside the house because it's insulated. But if the roof loses energy to 0 Kelvin, it's going to get colder and colder and colder. But as it gets colder, it's going to start receiving energy by convection from the warm air at 20 degrees. I can calculate then the temperature of the roof just by doing a balance between how much energy is being lost by radiation to 0 Kelvin in space and how much energy is being gained by convection from the surrounding air. So here we have this energy balance on the surface. The Q out is by radiation, which we have here, and the energy in is by convection. So I can make one of these Q in minus Q out. Here you have Q in by convection minus Q out, that is radiation, and is T surface minus 0 Kelvin, more or less. And the emissivity is more or less 0.9, as we have discussed as a typical case. The convection coefficient, let's say there is no wind, so it would be natural convection, that is a factor of 10, convection coefficient of 10 watts per meter square Kelvin. And what do we get in this case is that under natural convection, the surface of the roof would be at minus 6 degrees. This is amazing. The roof is at minus 6 degrees, but the air is at 20 degrees. This is one of those cases in which the surrounding temperatures are different than the temperature of the fluid. Fluid, 20 degrees. Surrounding space is 0 Kelvin. There are subtleties because this applies in environments that are dry. If we have moisture in the air, like for example in tropical places, the moisture takes the radiation, and the surroundings in this case is the same temperature of the fluid. But if the air is very dry, then you just go straight out into outer space, radiating energy. And this is really cool. Now, if we were to have wind, the convection coefficient would be 100. So the effect of convection, the heat in, would be much higher. And if we do the same balance, again, we end up that the surface of the house, the surface of the roof of the house would be at plus 16 degrees. Isn't that interesting? So if it is windy, it's going to be no frost. If it is not windy, there can be frost. I have seen this myself. I was always curious in Argentina, why if we never have snow and it's never below 0, why do we have frost in the morning? Now you know. I think super cool. It's 1:50, we're just in time. We're gonna stop here. I'll pick up at 2 with office hours, and we'll continue on Wednesday, making differential control volumes in the presence of conduction. Thank you, and I'll see you in a few minutes.